So let's verify that. H is equal to HH. So let's verify this. H is equal to HH. Okay. Since lambda H for each H in H, it's a bijection from H to H, and it's defined by x lambda H is equal to Hx. Okay, this is the definition. So to prove using this bijection, we'll show that H is equal to HH. So what is, let's take say Z belongs to H. Okay, let's take Z belongs to H. We'll show that this Z is of this form, H, element of H into H. Okay, so this Z is in H, which implies that its image is Hz. Okay, that's again in H. Its image is Hz. Okay, that is in H. Okay, I want to show that this element Z is in HH actually. That Z should be HH. So how do I do it? This Z is in HH. Okay, so let's take Z in H. Then this since we have a bijection from H to H, so that means there exists some x in H such that x lambda H is equal to Z, because lambda H is aunt. Okay, so this is the reason. So, but by definition of this Hx is equal to Z, so that means Z belongs to H. Okay, because X is in H, so Z is in H. So thus we have H is subset of HH. Now on the other way it's trivial. Now let's prove its reverse inclusion. Okay, so now assume that this Z belongs to HH. So this means this Z is equal to H into X. Okay, where X for some X in H. But then this Z is equal to Hx. This is since this lambda H is a bijection. Okay, this Hx. Okay, this Hx is in H. This is this Hx is actually X lambda H. Okay. So this is here H. Sorry, this is X here. X lambda H. This is X lambda H. Okay, this time. But X lambda H, it's lambda H. Okay, this is in H because lambda H, you have seen this is a map from H to H. Okay, so that's this Z belongs to H. Therefore HH is subset of H, and hence we have H is equal to HH. So next we verify that H is equal to HH. So that's the next part. Now let's verify that. Verify this one. Verify this. H is equal to HH. So again, since here we have rho h from H to H, defined by rho h of X is equal to XH, is a bijection. Okay, now let's prove H subset of H. Now let's take H in H. Sorry, not H because H is already there. So let's take, say again, Z. Let's take Z in H. Let's take Z belongs to H. Okay, Z is in H. So we show that Z is in H. But if this Z is in H, then its image is again in H. We'll take its pre-image, okay, because this lambda rho H is a bijection. So there exists X in H such that X rho H, image of X under rho H, is equal to Z, because rho H is onto, So this implies your Z is equal to, by definition of rho H, it's XH, but XH is an element of an element of HH actually, because X is in H. This belongs to H. So therefore H is subset of HH. Similarly, we can show that HH is subset of H. You verify this. So this is an assignment for you. Verify this thing. So thus, hence your H is equal to HH for all H in H. This also gives this gives H square is equal to H, and hence our H is a subgroup, is a subgroup of, this is a subgroup of a semigroup S, okay, as correct. Okay, this proves this section. Now our next section is regular D class. So here is a corollary of this section, and what's that corollary? Let if E is an idempotent, if E is an idempotent, if he is an idempotent in a semigroup S, then H class of E is a subgroup of S, and moreover no H class, okay, no H class of S contains more than one idempotent, Okay, this is the statement, and the proof follows from previous proposition, because in that case you will see that the intersection of H and H square is non-empty, because E belongs to both H as well as in H square. So let's see its proof. Since E belongs to H and E square is equal to E, it belongs to H square, so therefore H square intersection H is non-empty. So by Green's theorem, H is a subgroup. It's a subgroup of S. So moreover, no H class, so let H be any H class of S. So if H does not contain any idempotent, then we have nothing to prove, because we have to prove that no H class contains more than one idempotent. If H does not contain any idempotent, then we have done. So assume now assume suppose it contains two. We show that it contains at most one idempotent. Okay, assume it contains two idempotents. Assume E and F be idempotents in H, then E and F are both identities of a subgroup H, okay, which therefore E must be equal to F. So hence every H class contains at most one idempotent, contains at most, या तो इसमें कोई idempotent होगा ही नहीं, या अगर होगा तो एक ही होगा, at most one idempotent.